President Walkes.
They come in from the back, but I don't see them, you know? Okay, everyone! Hello. I see you back there. You're like, Okay. So welcome, everyone, to the final presentations for a bunch of our summer research program students. We have 5 presentations from the inaugural AOS summer research program, as well as 2 other students who joined us this summer who are basically AOS SRP adoptees at this point in time. So they're going to talk to you about all the awesome research that they've been doing this summer. So like I said, we have a really nice lineup of 7 different presentations, and Claire is going to go ahead and introduce our first speaker. So thank you.
Without further ado, here's Pamela presenting cold anomalies in the North Atlantic.
All right, take it away, Pamela.
Good morning, everyone. My name is Pamela Doran. I am one of the summer interns here in the AOS department. I've been working with Liz Maroon this summer, and we've been studying cold anomalies in the North Atlantic. So some of the background and motivation for our research can be based off of a couple of different papers. Specifically, the figure on the left is taken from the first paper I read this summer. It was Josie et al., and it talked about this cold anomaly that occurred in the Atlantic Ocean in 2015. This was titled the Big Blue Blob. I really like this name. It just makes it easy to remember what we're talking about. And to study these blue blobs in the ocean, we, for our research, used the Community Earth System Model 2. And on the right here, this kind of shows like a breakdown of all the components that go into this system model. For our project, we were specifically using we were using pre-industrial control simulations. So a little bit more insight from a couple other papers that we read. These kind of helped me get an idea of what we were supposed to be looking at. So again, from Josie et al., they kind of gave a breakdown of what the surface temperatures looked like, specifically the percentiles for that 2015 occurrence. And it can be seen that right above that blue blob in the ocean, there was some of the lowest temperatures ever recorded. And then one of the other things that we were looking at is, are these cold anomalies that are occurring due to atmospheric forcings, or are they because of a slowing of the Atlantic Maradona overturning circulation? And from Dreyfus et al., they did a historical run of the Community Earth System Model and found that there was a positive correlation between the slowing of AMOC and the temperature coolings that we see. So our goal for this project was to determine what cold anomalies look like without greenhouse gas emissions. In a lot of other papers, it can be seen that cold anomalies in the past have been due to atmospheric forcings, and projected cold anomalies of the future are mostly due to the slowing of AMOC from greenhouse gases. So we really just wanted to take a look at the pre-industrial data and see what these cold anomalies look like without any rising greenhouse gases. So first we wanted to select that area that these cold anomalies were occurring. So took just a weighted mean of the global temperatures, kind of zoomed in on this one specific area, and then of that area for a span of 2,000, I guess you could say 2,000 years of pre-industrial control. We wanted to find when this specific area fell below a negative 1.5 degrees cold anomaly. So anytime that this specific area fell below that threshold, we wanted to plot what other variables looked like, and kind of determine whether these cold blobs are atmospheric forced or forced by the slowing of AMOC. So over that span of the 2,000 years that we got from the pre-industrial control, we found that there was actually 46 occurrences when that temperature of the subpolar North Atlantic fell at or below a negative 1.5 threshold. And it can be seen that these are kind of spread out, so it's not like it was one big clump of cold years. This is over a time span of 2,000 years, so there's a couple here at the beginning, but then it drops down really low here. So just kind of interesting that it is more spread out and only 46 times that it was below that temperature. So when we took the weighted mean and kind of averaged it out and created a global plot, this is what this 46 occurrences turns into one big cold blob of the surface temperature in that subpolar North Atlantic. And I thought that this was interesting because anytime that it was less than negative 1.5, it looked as though the whole Earth was just kind of cold. It was just kind of like a cold spell. But I thought it was really interesting that when the threshold was set to negative 1.5, you can still see that there are some areas on the rest of the globe that are a little bit warmer and not just completely cold as well. So one of the other variables that we looked at is ocean circulation. Specifically here, we're looking at barotropic stream function. This can kind of be thought of as this plot. The easiest way to think of it is the rotation of the subpolar gyre. This dotted line here just represents that the subpolar gyre normally circulates in a counterclockwise fashion. And so these contours represent the climatology, how we would normally expect them to react. And then during these cold blobs, we can see that this red coloring shows that it's actually slightly rotating clockwise or is slowing down. So not going in its normal direction. And we see that again here when we look at the Atlantic meridional overturning circulation. So the best way to think of this plot is if you were taking a slice of the North Atlantic Ocean and looking at a vertical display. So we have latitude here, and the subpolar gyre is mostly in this area, and this just kind of goes by depth. And normally, again, these contours would represent that the overturning circulation would flow northward at the surface and then kind of come back and flow southward at depth. And these blue coloring signify that instead of flowing in that sort of normal clockwise rotation, there's a slight counterclockwise, or again, just kind of slowing of the circulation in general. Some other factors that we looked at were pressure and heat flux. So in this subpolar North Atlantic, again, we see a large pressure gradient over the North Atlantic here. This creates a really strong jet, and therefore we have ocean cooling by evaporation and sensible heat. With a large jet stream, we would expect that there would be ocean cooling by the atmosphere. So here we have heat being taken up by the atmosphere, and this creates a negative surface heat flux anomaly. So in conclusion, then, for the composite analysis of the 46 occurrences, we can see that it does happen that cold anomalies can occur without greenhouse gases. AMOC and the subpolar gyre weaken in the mid-latitude and northern hemisphere during these cold blobs, and sea level pressure shows stronger jet streams during cold blobs, which leads to ocean cooling of the atmosphere. One thing we didn't quite get to, and hopefully we could do further work, is to determine whether the AMOC and the subpolar gyre are contributing to this cooling that we're seeing, or if these are also forced by atmospheric, or if these are also due to atmospheric forcings as well. And that was all that I had.
Any questions for the speaker?
Yes, I have one. Pamela, very nice. What's the idea behind the atmosphere slowing down the Atlantic meridional overturning circulation? How does that work? Because let me just throw something out from a naive point of view. I know nothing about this. If you have a consistent cold air outbreaks over the Labrador Sea and you're cooling the surface water, I would think that is going, and that would happen with your low sea level pressure anomaly in the southeast of Greenland. I would think that accelerates the overturning circulation by making the water at the top negatively buoyant by heat loss. How do I think about that?
Oh, that is a good question. Okay, so this was explained to me towards the beginning of the summer, and I I may need to refer to my advisor, but I believe. Okay. So it's due to the I believe like the density changes. So there's a bunch of different factors that go into why we see the overturning circulation slowing. And I think from what I've read and seen, most of it kind of actually is deal with the freshening of the water. So it creates less dense water, and so it's kind of slows it down, especially due to ice shelves melting and stuff near the subpolar gyre. So when you have that fresher water, it doesn't rotate, overturn as quickly as it would. That was one factor that I wanted to look more into, and we had read some papers on about how the freshening is influencing the slowing of the overturning circulation. But unfortunately, we weren't able to get all of the salinity pre-industrial control in at once on time as well. And I unfortunately have also been sick for the past couple of weeks, so I was not able to get that far. But that is a good question. I think for the most part, as far as the slowing goes, there's a lot of factors, but freshening and has a lot to do with it.
Okay, thanks.
We have time for one more question. Anybody?
Yeah, this might also be a question for your advisor, I'm not sure, but I noticed, I don't know anything about the pre-industrial control. You've got 2,000 years of simulation. It looked to me like in the plot of that anomaly versus time, that there was actually a trend in that. Is that a real trend, and is that traceable to any specific data set that goes into that pre-industrial control, or where does that come from? Or maybe I'm just imagining that I see it.
Sorry, which plot did you want me to look at?
So if you go back to the plot of pre-industrial control anomaly versus time, where you showed where these anomalies showed up, so it's a time plot.
Oh, the time series?
Yeah.
Yes. Okay. This one?
Yeah, so when I look at that, yeah, that's it. So when I look at that, it looks to me like there's actually a significant trend over those 2,000, however many years that is. And I'm just wondering whether that's a real thing, or it's just the model drifting over time.
So from my understanding, it is just kind of like a model projection, but it's a pre-industrial projection. So it's taken from the Community Earth System model, and they have a pre-industrial control that we used in order to determine all this. I don't think that's why, unfortunately, I don't have like specific years, because I don't think this is based on actual data. This is supposed to be, thousands of years in the past based on of the pre-industrial control that we got from the Community Earth System model.
Okay, thank you.
No
Okay,
problem.
thank you very much to our speaker.
Pamela, I'll let you go.
Okay, so I'll join
Great
that.
job. We'll see you on YouTube, okay?
Okay, sounds good. Thank you.
You gotta let us know who our next speaker is. Can you also take pictures? Do you have a phone?
I just use it for.
Oh, type, yeah.
And John, freshening cold laws or fresh laws, so that's one possibility. It's also uses simultaneous, so it's wind force.
Okay. How much cooling is required to overcome the freshening effect on points?
Depends on the model.
Oh,
That's an excellent question. Some models are different ways to model it, the other, some that's an issue.
okay,
That's
okay,
a research question, depending on how the model is falling in that way.
okay, thanks.
Because it's more than one theory.
So if anybody in here wants to take pictures too, please do. We're gonna crowdsource this.
Okay, our next speaker is Idamis, talking about impacts of the different types of El Nino on the Caribbean precipitation.
You hear?
Mhm.
Yes.
Cannot hear?
Hello? Yes?
Yeah.
Yeah.
With the microphone?
Yes.
Mhm.
Okay. Well, good morning, everybody. Well, good morning, everybody. My name is Idamis Rodríguez. I'm from the University of Puerto Rico at UW-AOS campus. And this past month, I was working with Dr. Victor Chavez and Dr. Angel Idamis, and we were studying the impacts of the different types of El Niño in the Caribbean region. And when we are talking about El Niño, we are talking about the warming of the sea surface temperatures in the tropical Pacific. And El Niño is a very important climatic phenomenon because it changes the global atmospheric circulation and also affects the precipitation and temperature across the whole globe. But before we know a little more about the El Niño, we need to know what is normal. And the normal conditions, as we can see in the figure, we are going to see trade winds that are moving from the east to the west, and they are going to bring the upwelling and going to bring up cold water with rich nutrients for the fish, specifically in the area for the coast of Ecuador and Peru, which are good for the economic. And also the trade winds are going to have warm waters at the west of the Pacific region. And that warm waters are going to bring moist bracing, and we're going to have convection. And heavy rain is going to be there at the west of the Pacific Ocean. And when we are having rising air, we are going to have also sinking air at the east of the Pacific region of the coast. And now that we know a little more about the normal conditions, which in general, these are the worker circulation, El Niño is going to alter this circulation when we are now going to have a low pressure over the eastern Pacific region, as you can see in that figure, and we are going to have rising air and heavy rain. And then, on the other hand, we're going to have dry conditions with a high pressure over the west of the Pacific region. And the differences between those two pressures are going to weaken the trade winds, and now are going to bring the direction of the wind from the west to the east. And that is how El Nino is going to work. It's going to alter the normal conditions, and we are going to have very warm waters at the east of the Pacific, and the fish in that area is going to feel damaged. And what are the impacts of precipitation? And this answer can be answered saying that depends with the region and the season. For example, here in the figure, the color yellow in South America, we are going to have dry conditions, as the color yellow shows us, for the whole year. And then we are going to have at the southern of the North America, the blue color, we are going to have wet conditions only for the season till September and February. And then we want to focus in the Caribbean region, but what is going to happen? It's going to depend, because we are going to have different impacts that are impact in the season. For example, in the Caribbean region, as you can see in the red circle, we are going to have wet conditions only for the season from January to April. And then we are going to have dry conditions for June and October. And this is the evolution of El Nino. In the first image, we are going to see the beginning phase of El Nino. And as you can see, the sea surface temperatures are not very clear during the month of April. Then, on the growth phase of El Nino, we are starting to see the sea surface temperature starting to warming. And we are going to have a maximum convection over that region when we are having the warming of the sea surface temperatures. And we are going to have the rising air over that area, and we are going to have sinking air in other parts of the world. Then on the mature phase of El Nino, we are going to have like the peak of the event that is going to be in December. But of course, the response of these types of phases of El Nino depends on the region and also depends on the season. So, as I said before, El Nino can cause different impacts around the world, which depends in the region and the season. And in the figure that we can see in the PowerPoint, we are going to be focusing in the main objective of this study that is going to investigate the impacts of the different types of El Nino on the precipitation in the Caribbean region. So how do we do that? We do that with data of precipitation that was obtained from the Climate Hazards Group's infrared precipitation with stations, which is called ships. And this rainfall data was estimated from rain gauges and satellite observations. And the period that was considered for this analysis was from 1981 to 2018. And also, we use E-index and C-index, where basically these two indices summarize the Ensemble variability in the Eastern and Central Pacific region. And as you can see in the figure, the Eastern Pacific is the top figure. We are going to see the warming of the sea surface anomaly in the Eastern Pacific. Then at the bottom, we are seeing the Central Pacific El Nino, when we are seeing the warming of the sea surface temperatures anomaly only in the Central Pacific El Nino. And basically, these indices are documented in Takahashi and are available in that web page. And also, we use the Pearson correlation coefficients were calculated to determine how the two variables, the precipitation and the indices, are associated. And we also use the test significance to see the correlations between both variables. And these are the results that we obtained. And as you remember at the beginning, the onset is the beginning phase of El Nino that goes from March to May. And especially in the month of April, we were watching like the sea surface temperature were not clear. So when we have the Eastern El Nino, we are going to have this result, as you can see in this figure. And when we are talking about the Central El Nino, we have that result. And to understand a little bit about the legend, the red color shows us dry conditions when we are not going to have precipitation, while the blue color shows us precipitation. So the eastern El Nino, when we are having these beginning conditions of El Nino in the eastern, we are going to have a negative correlation in Cuba because we are going to have dry conditions. And on the other hand, we are going to have like a positive correlation only for La Española and Puerto Rico during the eastern El Nino, that is not significant. And on the other hand, when we have the beginning of a central El Nino, we are going to have a positive correlation between the sea surface temperatures in the central and the precipitation, but it's not really significant. The only significant place is in Jamaica. Then on the other season that we're studying in the Caribbean is the growth. And as I said before, the growth is when we're starting to see the sea surface temperature started to warming up in the Pacific. And in the eastern El Nino, we have, and the central El Nino, we have kind of like a strong and significant correlation because at the central El Nino, we have dry conditions in the whole Caribbean, and it's very significant. While on the other hand, in the eastern El Nino, we have the same behavior, but it's not significant. Lastly, the last phase of El Nino, which is the mature, from their season that goes from December till February, we are watching like the same behavior. We're going to have a positive and significant correlation between Cuba in both types of El Nino because we're having a positive correlation. So we are going to have precipitation over that area when we are having a peak of the event of El Nino. And then we're going to have a negative correlation in both types of El Nino for La Española and Puerto Rico, but it's not significant. So we are going to have dry conditions. In general, the ESO events can occur over different regions, as I said before. And these events can be classified as the two types of El Nino, the eastern and the central El Nino. And when these anomalous conditions are recorded over the eastern and the central, and these different types of El Nino can cause different impacts on the precipitation on the Caribbean, which, as I said before, depends on the season. So that's everything. If you have any questions. Yes.
So very, very nice study, and it's nice. It seems like this data analysis is leading to questions about, you have your standard picture of the atmospheric circulation in the equatorial Pacific, but now you're showing it's not really a teleconnection, right? We think about teleconnections affecting mid-latitudes, but is there some other more direct circulation that is impacting Puerto Rico? Have you thought very much about that?
Yeah, that's also a question that we make when we have these kind of results, because this is only El Nino, but we can also have other events that are present in that season, so it depends. So we have to kind of look for every season very close to see what can be other teleconnections related to that behavior that we are seeing. Yeah, we have like more questions about the results than answers.
That's the best kind of.
That's a good research project. Right.
That was a really good presentation. I do have a question about the data set. Does it remove signal for hurricanes, or is it just all precipitation in the area?
It has all the precipitation in the continent, in the area specifically. So we don't have here the precipitation that is covering the waters, for example. So
My question's somewhat related. I'm interested in the non-significant increased precipitation regions. Are there differences in the type of systems that bring the precipitation under those conditions? And are they, so are they related, and maybe there's another way to stratify the data?
That was my line of thinking.
Oh, okay.
Yeah.
Can you repeat again the question?
Yeah, you can imagine that it might rain on La Española from a number of different mechanisms, tropical clusters, just isolated afternoon thunderstorms and so on. And if you could categorize them in distinct ways, might some of these differences in precipitation, not dryness, but precipitation, actually start to show you something more about what's going on under either eastern or central El Nino conditions?
Okay. I understand the question, but I don't really know how to answer that.
Yeah, I guess
That's
it's not
a really
really
good question. That makes me think.
it's along the lines of what you said earlier, that you have more good questions after your research
Yeah.
project, which you should have, and this is one that kind of strikes me. So it's not really one to answer. So.
Any other questions?
So you're looking at two different kinds of El Nino events, and when you're looking at El Nino, you're already cutting out a certain amount of time because you're only looking at part of the time frame, and then you're splitting it into two events farther. I was wondering how much data do you actually have to split those two events, and like how your statistics, if you have more events, you're going to be more sure of what's happening. Are there enough Central Pacific El Nino events to be really confident in some of these results?
That's also a good question. So maybe you're questioning how if we have more central El Nino and more eastern El Nino.
Yeah, like how many of each event do you have?
Okay, so I have a figure over here, and this is like the monthly indices of the top is the east central El Nino, and the other one is the central El Nino. And I don't know if you can see the red lines that go up to bottom, and it's kind of a mix. For example, the eastern El Nino, the red color, it shows like the extreme events of El Nino at the east. And with that question, we have like more central El Nino extreme events, as you can see in this figure. So I think it's going to be more the central El Nino that is going to be more present in the Pacific region.
Thanks. This is a really great figure.
Let's thank our speaker.
Okay, next will be Bering.
Did you take pictures? I have her phone. And she has my phone. Tú le estaba texteando y yo. Así me estaba texteando. Y tiraba de foto con la todo porque como que se ve. But Hannah took photos.
All right, everybody ready to transition to our next speaker? Am I ready, Brad? Okay. All right, we're ready to go. Take it away, Derek.
Is the mic working?
Yes.
Yeah.
Okay. All right. My name's Derek Sue. I am part of the Atmospheric and Oceanic Science Summer Research Program, and I'm from the University of Northern Colorado as a senior. And this summer, I was assigned to work with Ankur in the lab of ecometeorology, and we studied the impact of meteorological conditions on lake effect snow occurrence over Lake Superior. So, a little introduction about what Lake Superior actually is. It's lake effect snow occurs due to lake-atmosphere interactions, producing snowstorms over nearby regions. So the region I studied was the Upper Peninsula of Michigan, and these blue arrows are indicating the wind paths of these air masses going over Lake Superior. And there are several atmospheric conditions that are necessary for these events to develop, which we will see later, but including those, there's fetch, which is the distance that the wind travels over the lake, as well as ice cover of the lake. and these are necessary for lake effect snow to develop. Yet there's inconsistencies between the expectation of these storms to develop and the actual occurrences of lake effect snow. And so the goal of the study this summer was to quantify the mismatch between the expectation and occurrences of lake effect snow and determine the favorable conditions for these. So a little outline of this presentation. First, I'll go over the motivation behind my work, the data and methodology I used, the results, conclusions, and further questions and work. So a little motivation behind work. When I came here this summer, Occurrence provided me with a different research project that focused more on the biology side of meteorology, and I was more interested in the atmosphere side of it, so I went with this project. And then I also chose the lake effect snow project because I have, I think, a lack of knowledge in that field, so I wanted to pick that and learn more about it. In the research region that I'm studying, it's kind of near from where I'm here this summer, so I wanted to pick that as well, just to study the impacts of lake effect snow, and then we hope to draw conclusions on how the impacts of atmospheric conditions can impact the frequency of these events. Starting off with data and methodology, so we grabbed various data sets from all over the place to study and look at the important atmospheric conditions necessary for lake effect snow development. So we grabbed, from the first place was the Keweenaw Research Center, which is part of the Upper Peninsula in Michigan. We grabbed temperature, wind speed, and wind direction, and the important conditions that we used was wind speed and wind direction for the surface. We grabbed data products from the ECMWF, ERA5, which was reanalysis data, and this included 850 millibar temperature as well as wind, speed, and direction. And then we grabbed ice cover and water temperature data from the NOAA Coast Watch Great Lakes, and this was just a buoy in the middle of the lake. And then I grabbed storm archive data for the events for lake effect snow impact in Michigan from the NCI Storm Events database. And this first table here is the typical conditions necessary for lake effect snow events to develop. And so these three conditions were from the literature that I read, and these are what people typically look at to determine if lake effect snow will develop. So this first value is 850 millibar wind speed, and we want wind speeds between 5 and 20 meters per second because we don't want the air mass to move too slow, or it's just going to dump all the snow in the lake. And if it moves too fast, it won't have enough time to pick up the moisture from the lake. Delta T between the lake surface and 850 millibars, we want that greater than or equal to 13 degrees Celsius. And vertical wind direction shear between the surface and 850 millibars, we want that to be less than or equal to 30 degrees because we don't want it to be too different between the surface and the air above. Continuing on with data and methodology, moving on, we grabbed those relevant atmospheric conditions and calculated and compared those to the storm events database to observe the average values of these variables during events. Like I said earlier, 850 millibar wind speed was grabbed from that ERA5 data product in the Middle Lake Superior. And delta T was calculated by grabbing the water temperature from the Middle Lake Superior and the 850 millibar temperature from ERA5, taking the difference between the two. And the reanalysis data was grabbed from the same point as the water temperature was grabbed from. And vertical wind direction shear was calculated by taking the surface wind direction for the Keweenaw Research Center and the 850 millibar UNV wind components and getting the wind direction from those in the ERA5 and taking the absolute difference between the two. Once I got those atmospheric variables calculated, I combined those with the storm events to see what the daily atmospheric conditions were observed from over Lake Superior from 2006 to 2020. So I used a binary system to assign ones and zeros to each atmospheric variable, ones being favorable and zeros not. So one represented the observed variable followed within that threshold based on that table we saw earlier for lake effect snow to occur, and a zero represented the observed variable does not fall within that threshold. The binary system was also then used for the expectation of lake effect snow events. So one represented all three criteria of the atmospheric conditions were met, and a zero represented one or more criteria of these conditions were not met. And then I also used the binary system for the occurrence of lake effect snow. So one represented an event was observed on that respective day based on the storm events database, and a 0 represented an event was not observed on that day. And lastly, I used the binary system to classify each quadrant for this 4-quadrant plot we'll see in a little bit, and that compared lake effect snow occurrence and expectations. So one represented that criteria met that specific quadrant's classification, and a 0 represented the criteria did not fit that specific quadrant and thus fit another quadrant. So moving on to the results I got, the 4-quadrant plot was created that compared lake effect snow occurrence and expectation. And lake effect snow was expected to occur when all 3 of these conditions were met, and it was not expected to occur when 1 or more of these were not met. So these are the plots that I got on the right, comparing strict conditions to loose conditions, and I'll explain this. So strict conditions were representing that the conditions were met all the criteria from table 1, so I met the 850 millbar wind speed, delta T, as well as a vertical wind direction shear. And that is that top right plot right there. And loose conditions represented the relaxation of these criteria. So delta T was relaxed to only having to be greater than or equal to 12 degrees Celsius instead of 13. And vertical wind direction shear was less than or equal to 35 degrees instead of 30 degrees. And so the plot, or the quadrant that we're most interested in, is quadrant 2, because that is representing lake effect snow to be expected based on the conditions, the atmospheric conditions, yet we're not observing any events. We want to look at the reasoning for that why. And so the bubble in each quadrant is illustrating the percentage of lake effect snow occurrence for the days out of the total days examined. And this was between November 2006 and March of 2020. Moving on to the conclusions I found from these results. As we'll see in a little bit, the important atmospheric conditions were based on a composite analysis, and these were the average atmospheric variables compared to lake effect snow occurrence. And I found that based on the events, blue being event was observed and orange being there was no events observed, delta T and ice cover percentage seem to have a more important factor in the frequency of these events, whereas 850 millbar wind speed and vertical wind direction shear did not play as important of a role. For example, ice cover, when there was no event observed, was about 20% of the lake, and when there was an event observed, it was about 9% of the lake. And differences between the lake effect snow occurring versus not occurring is plotted below. So ice cover percentage is about 11.53% difference between the two of events occurring and not occurring, and delta T was about 1.89 degrees Celsius. Some lessons I learned were that lower ice cover percentage of the lake is necessary for an Arctic air mass to pick up the warm moisture from the lake superior. If it's too covered, then there's no water for it to pick up. No lake effect snow event was observed, even though it was expected to occur due to a higher ice cover percentage in the composite analysis that we saw. And understanding these atmospheric variables will assist future generations of forecasters. And I found that we could start creating a threshold of ice cover percentage necessary for lake effect snow development, because based on the literature that I read, no one really talked about the necessary ice cover percentage that would determine an event or non-event. So further questions which could lead to further work were, how can the study of Lake Superior be applied to the other Great Lake regions? Can other atmospheric conditions besides ice cover be responsible for lake effect snow not occurring, although it is expected? And these can include aerosols for cloud condensation nuclei, lake air gas exchange, and turbulent mixing. And how can future forecasters better understand these conditions to better be able to put out earlier warnings for these events and impact to regions? I'd like to give a special thanks to Ankur, Andy, and Serena for their support in this research. These are my references. That concludes my presentation.
I'd be keen to see the 4-quadrant plots again. I'm not sure if I understood that right. So like on the top one, just the bottom left, that tells me that in the vast majority of cases there was lake effect snow was not expected and it did not occur.
Yes, that's correct.
Okay. So in very few cases was lake effect snow expected and occurred?
Yeah.
And why do you think that is? There's so few cases that were predicted well.
I think it could be maybe because we set it where all 3 of the atmospheric variables had to be met. So maybe if I had more time, I could see if only 2 of the variables had to be met, because I did see events in the database, or not the database, the data that I saw, where like only 2 of the events were met, but I still saw an event. But I only set it to where 3 of them had to be met, so that kind of excluded those and put those in a different quadrant. So if I had more time, I'd probably change those conditions around.
I mean, I think it was a good idea to loosen the delta T. I might even take that condition out completely. You might find that you don't get as unstable conditions on Lake Superior as you expect. Like a lot of the conditions that you're talking about come from Lake Ontario, like what, Nisiol 95 or something like that. It's different probably. Yeah. Might be in those good thought.
Yeah, I think building on that, I wonder if you could kind of do this study in the reverse too, right? Which is take all the events and then kind of build some sort of algorithm that determines the effects. So do you think you have the data to be able to do that?
Yeah, if I just had more time, I probably could have. I was just stretched for time, so yeah.
Right, and our original hypothesis here, you're really interested in quadrant 2 because you have these hypotheses that cloud condensation and aerosol with VOC emissions from lakes are important for preconditions for LES that not understanding. So this gives us really great fodder for where we might potentially run a field experiment or do additional analysis of cases. So thank you for doing this.
And the condition of ice cover is like a global boundary condition for the whole lake. And one can imagine that local fetches, local locations, with respect to fetch, it may be we have fairly high ice cover content percentage-wise. It doesn't make any difference for snow in one particular location along the coast. So if that could be partitioned out too, you might, along the lines of doing it backwards, it'd be really interesting to find that out.
Okay, thank you. So our next speaker will be Riley, presenting using a drone to validate ground-based remote sensing of atmospheric temperature and humidity.
Nice job.
Because we're all long-winded.
All right, is the mic working?
Yep.
All right. So I'm Riley Jackson. I am a student at the University of Northern Colorado, and I was an intern here with the AOS Summer Research Program. And my project was using a drone to validate ground-based remote sensing of atmospheric temperature and humidity. And I worked with Grant Petty and Tim Wagner in order to conduct research on this topic. So a little bit of, I guess, like background and motivation for this project. So the overall motivation of this project was to evaluate whether the variability of area observations over time was due to fluctuations in environmental conditions or if it was an artifact of the retrieval. And this was something that Tim brought up. So there were, so on a profile-to-profile basis, there were fluctuations on each of the different observations with the area. And so I guess next I will present what like the area and the measurements that we're going to be using to conduct the project. So the area is a ground-based remote sensing tool that retrieves profiles of temperature and water vapor up to 3 kilometers in the atmosphere. And it can be used for forecasting purposes or for figuring out observations. And it has the advantage over a radiosonde of being able to have observations in a central point. So like a few weeks ago when we launched a weather balloon, radiosonde flew away, and this essentially means that we can have data at a central location, and it also is relatively inexpensive compared to a radiosonde, where we are able to get observations without having to launch a weather balloon every 30 seconds, for example. So, and then in order to validate whether the area is seeing correct observations, we used a drone with an IMET XU2 attached. And so the IMET XU2 is able to provide direct measurements with temperature and mixing ratio, as well as pressure. And the purpose of the drone was to take measurements at a certain height. So as I mentioned earlier, with the radiosonde, it flies away because of the wind, and so it will drift, and it won't take measurements at a certain height. So with the drone, we're able to take measurements at a certain level and not have to worry about having the weather balloon fly away and conduct data higher up in the atmosphere. And so the fixed level that we flew the drone at was 114 meters above the roof of the AOS building. And so this corresponded with one of the levels, the height levels that the area measures at. And so this was the highest that we were able to fly at without violating FAA regulations. And so we had a total of 10 flights over a period of 5 days. And so we attempted to gather data from different times of day. So there were potential issues with like mixing. We had to stop a few of our flights because it was windy. And so we had a couple of flights earlier on in the morning where there wasn't as much mixing in the atmosphere. And this also helps to provide a profile of the drone where we can see the temperatures increasing throughout the day, and if the drone and the area respond to that. We also wanted to have a potential, I guess, like just different temperatures and humidity profiles in order to make sure that the drone and the area are responding to varying conditions. To the best of our abilities, since the research done was during the summer. And something else that we also had to take into account was that the drone data and the area both had different time intervals. The drone data was taken every second, while the area observations vary between 10 and 40 seconds. And so we had to match the area and the drone data. We took a 30-second average of the drone data based off the area data points. And so we did this before and after each data point. And this helps to take out some of the outliers that were occasionally present in the data, which can be seen in the second figure of the mixing ratio, where the drone did see a couple of outliers that were possibly due to factors such as, we flew this pretty close to the power plant that's nearby, and so that may have affected the mixing ratio. And so some of the outliers just weren't correct with the data. If we took an average of this, it helped to get rid of some of the outliers. And so we plotted these for each of the 5 flight days. And so the overall results of our flights, we do see that there is a strong correlation of temperature data, which indicates that the area temperature would be representative of the environment because both the drone and the area are seeing very similar temperature values. So the correlation was almost 1-to-1. It was 0.99. And so what this tells us is that we're seeing 2 different data sets that are producing very similar temperatures. However, this was not true with the mixing ratio data, and it had a weak correlation. And this is indicated in the graph on the right, where the data was certainly not 1-to-1, and the area data almost had a vertical profile. And what this indicates is that the drone had a significantly larger, or the area had a significantly larger range compared to the drone, where the drone had a fairly consistent range. And so going back to the research question, essentially this means that the area likely had a lot of variability. And this is a potential issue. And if this was a part of the environment, we would see that the drone data would also be having a significantly larger range. And if we look at some of the standard deviation values as well as the mean, we see that this further backs up this point, where essentially the mean for the temperature and the standard deviation are both very similar. However, if we look at the standard deviation for the mixing ratio values, we see that the area had significantly more variation compared to the drone data. We see that the area standard deviation is significantly higher compared to the drone, which indicates that the area is seeing a lot more variation. And if we continue to kind of look at the mean bias and RMS difference, we see that the temperature had a strong correlation on all 5 days, and that the mean bias and RMS difference was near 0, which indicates that there weren't any significant biases, and RMS difference also indicates that the temperature was generally optimized. And this was not true as well with the mixing ratio, where there's a higher mean bias, and so this means that the mixing ratio data generally was seeing higher, the area was showing more moisture in the air than was indicated by the drone. And this essentially means that this was not representative of the true environment, and that the mixing ratio data was generally not optimized. And this can be further seen with a few histograms here, where essentially you want to have a modal value of 0, which indicates that the area and drone data are generally uniform and that they are showing similar things. And this is true for the temperature. It's very difficult to get like a perfect data set, but the temperature does show that the modal value is very close to 0. And this indicates that it was generally uniform and there wasn't a large amount of spread. However, this wasn't true with the mixing ratio, and it was a little bit concerning to see that there were significantly different values, and the modal value was 2. So this indicates that the area is showing a higher mixing ratio value and is showing more moisture in the air that would be indicated by the drone. And so the overall conclusions is that the area temperature data is representative of the overall environment, and that the variability of area observations with time weren't shown with the temperature profiles. However, the higher standard deviation and the weak correlation, along with the higher RMS difference and mean bias, indicate that there were potential fluctuations in the area that were not shown with the mixing ratio values. And that indicates that this is more of an artifact of the area retrieval, not indicative of the overall environment. And so there are a couple of reasons for this. One of them is that the area has to take measurements of temperature and mixing ratio at multiple different levels. And so this indicates that the drone is only taking data at one level, and you also see this with a radiosonde. It's only taking data at one single point, whereas the area has to account for multiple different levels up to 3 kilometers. So this was just one data point. And this can lead to issues with data collection with the area. And there's also a physical reason for this. When you're taking infrared radiation that the area is producing, and it's going up in the air, and you're seeing more water vapor molecules, this can lead to more reflection, and this leads to greater scatter with the water vapor data. And as well, there is probably like more questions to this data and more further research that can be certainly done here. So we can see like measurements at different heights, some additional reasoning behind why the mixing ratio was so inconsistent. And we only did this during the summer months. And so it would be interesting to see data with colder or warmer conditions. There are also potential issues with seeing higher mixing ratio values than we saw. We didn't get data during a particularly humid day, so it would be interesting to see how the drone would respond to that as well, since we didn't see any drone values above 10 grams per kilogram. And it would also be interesting to see how lower mixing ratio value would help at all with the variability with area. And there are also questions if temporal coherence can be added to the area retrieval to reduce profile variability. And there are also questions about how would this affect forecasting or observations. So that is the end of my presentation. We manually flew it. And so Grant flew it. There were some potential issues, with like the wind and stuff like that. So, but for the most part, we were able to get it at a stable level. And so there weren't any real issues of getting it above at a standard level. So for the most part, the altitude was generally the same once it got up to about like 375 feet. So.
It was programmed in the sense that you could park it at one location and leave it there, it would stay there.
How far out of town do you have to go to be able to do vertical profiles of like 500 feet or 1,000 feet? Is there any place where you're not constrained by the FAA?
No.
Oh,
Not
that's
without a
too bad.
waiver, not without a waiver.
And that's a serious
That's a
endeavor.
serious, that's why I built an ultralight, so I don't have that.
Yeah. Because if you had profiles, you'd have some of the problems that you brought up, Riley, would probably disappear. And then you might have new ones, but you might have some of the ones disappear. Yeah. Okay.
So this might be more of a question for Grant, but, so the Aries, the Aries and Southern Great Plains, it's been validated against radio science for 20 or so years. So I would look at how your results, particularly for water vapor, compare with the previous pretty extensive validation with radio science. And then the second thing is, in situ water vapor is a very, very difficult measure to make. And I'm wondering what the accuracy of your sensor is and how it's calibrated. Is calibration, does that affect the bimodal or biases that you're seeing?
Well, one of the points that wasn't mentioned in Riley's talk is that we had wanted to do some calibration with the IMET XQ2 and measure, humidity and temperature under controlled conditions and not only look at bias, but also look at response time and things.
Right.
There just wasn't enough time to do that. And so we had to just kind of say, well, we can do that later retroactively and see how things look then. But it uses the same sensors as a radiosonde. It's actually IMET, or I believe the name of the company. The same company manufactures radiosondes that are also used in research. And it's the same temperature and humidity sensors. So in theory, whatever issues affect the radiosondes, apart from age, should be affecting this device as well.
So does it stay stable, or is it coming up and down? Because with the radiosonde, you always have the issue of finding the proper ascension rate, right, for the sampling. Is it the same issue with the UAS?
So the drone is very easy to just basically ascend vertically over a point without it moving. And then you get to the altitude you want to get to, and then you just park it there and you leave it there, and it will stay on station based on GPS and inertial measurements, and not budge from that spot really at all. And so you're really parking it like a tripod up at one spot and watching the atmosphere go by. Yeah.
Let's, we're gonna finish this later. It's all good. So give Riley another round of applause, please.
Yeah, Megan?
See you there. I know. We're gonna make it, it's gonna get all right.
Yes.
Okay, is this working? Can you hear me? All right. Yes. Okay. All right. Hi everyone. My name is Megan. I'm an undergraduate here in the UW-AOS department. This summer, I was assigned an Arctic oceanography research project. I worked with Professor Hannah Zanowski on this project, and I specifically looked at CMIP-6 model performance of Bering Strait transport variability. So a little outline of what I'm going to be talking about today is I'm going to introduce where the Bering Strait location is. I'm going to explain why this area is so important for study. I'm going to give a brief explanation of what CMIP-6 and what ensembles are. And then we're going to take a look at my results, which is showing a time series variability with trends, observational spreads, and then I'm going to make some final statements about this project and some conclusions I came to. So starting off, where is the Bering Strait? As you can see to the map to the right, the Bering Strait is a gateway between the Arctic and the Pacific Oceans, and it is located between the United States and Russia. The middle photo here is just showing a reference to Madison, where the Bering Strait is. And then I have a satellite view from NASA. It might be kind of hard to see, but here's land right here and land right here, so you can really see how narrow that strait is. That's what makes the strait so unique, is that it's extremely narrow and it is extremely shallow. It's only 50 meters deep, and if you know how shallow that is, it's pretty shallow for the ocean. So this here is just showing general circulation of the Arctic. You have from the Atlantic to the right, warm saltier waters coming over the coast of Greenland, and then you have a freshwater northward flow through the Bering Strait. And as you can tell, this is a very complex circulation system, which is why this area is so unique to look at. And with the really shallow area of water with increasing flow is a very interesting combo. So why do we care about the Bering Strait volume transport? When I talk about volume transport, I'm referring to the amount of incoming water flow through the strait. Like I said earlier, it's the only gateway between the Arctic and the Pacific Oceans, and it sets the properties of the Amerasian Basin. The flow is increasing very rapidly, so with warmer and fresher Pacific inflow, more heat is carried, which increases ice melting in the Arctic. And from other research papers that I've been reading, like Zanowski et al. 2021, she had concluded that most of these models are not agreeing with what observations are captured. So if you are not familiar with CMIP or CMIP-6 specifically, CMIP-6 stands for the Coupled Model Intercomparison Project Phase 6, and it is conducted under the World Climate Research Program. This program gets together every 6 to 7 years to see what advancements they can make to our climate modeling, which most of you know help us better understand what our climate is going to look like in many years down the road. CMIP-6 contains over 50 plus different models. I'm specifically only looking at 7 of these models, as you can see listed there. And within these models, they contain ensemble members. These ensemble members within just these 7 range from 10 to 32, and these ensemble members are just individual simulations, each creating their own trials of data. So in other words, I think of them as trial runs. And to be noted, these are historical simulations, which were run with historical forcing. So in other words, they were forced with the actual observations of the climate we have. And this figure to the left here is just showing the performance index of CMIP-6 on a global scale. So moving on to my results, this is 6 out of the 7 models that I worked with, showing a time series from 1990 to 2019 of model output comparing volume flux variability between the model ensembles and the transport observations. So it is just showing the internal variability between the ensemble members, which are the shaded gray lines, and the transport observations, which is the blue line. And these transport observations are from the climate station moorings acquired from Woodgate et al. 2021, and these are just buoys placed in the water throughout the strait. So to note here, when I refer to the internal variability, that is just the natural variations in our climate system. By just looking at these 6, you can see that there is great variability between all of them, but looking at MyRock 6 specifically in the top right-hand corner, you can see that that model is not even comparable to what the other models are capturing. So looking at the 7th model, the IPSL model, a little bit more in depth, you can see the large variability between the transport and ensemble members. Once again, we're comparing the blue to the gray. The black line is the mean of those ensemble members. You can see that the transport observations fall close to the mean, but compared to the rest of the ensemble members, it's not doing a great job. This is also not really showing an increasing or decreasing trend within the plot, so that is why I decided to figure out a way in which I could look at these trends, and I created box and whisker plots, which we'll look at in a second. And overall, these observations, the transport ones in the blue, are just supposed to be more comparable to those ensemble members in gray. And by looking at that, they're not comparable. So now let's take a look at the individual trends. This is for all 7 models. These are Decado Trends of model ensembles spanning years 1990 to 2015 of that volume flux, compared again to the transport observation trend shown in blue. So looking at the first decade, 1990 to 2000, there's a heavier negative trend than positive in the volume flux. You can see that blue dotted line there. And there's also a negative trend within the ensembles as well. And you can see there's a slight overlap between the ensembles and transport observations, but the means of those aren't very close. However, in 2000 to 2015, looking at the next plot, the trends within the models fall nowhere near the transport trends. You can see the transport observation line is way far to the right than what the ensemble members are capturing. Besides looking at the IPSL model right here, you can see this falls very close to the transport observations, but this may be because this model contains 32 ensemble members. The rest contain around 10 to 14. So maybe if the other models contain more ensemble members, they would fall closer to those transport observations. But we still overall here are just seeing that jump in increase in volume flux between the 2 decades. So I wanted to look at these trends a little bit more in depth. I wanted to see the spreads within these trends. So what I did is I created synthetic ensembles. So how did I create these and why did I do this? So I did this to better understand the spreads in these trends because there is internal variability within these trends. So I created these to show the spreads between that variability. Synthetic ensembles are resampling both the model ensembles and transport observations to see what trends there are and even if there are any trends. So overall, this just gives us a full spread of the internal variability, determining if maybe there's a forced response like climate change, which is making these models look like this. So what I did is I used a statistical technique called block bootstrapping, and this was a strategy used by McKinnon et al. 2017. And to better explain this strategy, Hannah Zanowski has provided me with a figure to better explain this process because it is quite complex and confusing. It took a bit for me to grasp onto the concept. So these figures are just showing what creating synthetic ensembles are. So you take a single ensemble member, which is shown in the red there, and you subtract the forced response. You resample the data, and then you plug that resampling in to the forced response to create the synthetic ensemble member. So these are just showing my results for my synthetic ensemble spreads. I took 1,000 synthetic ensembles and created to directly compare the spreads between the observational and model transports. So now the ensembles are in gray. The blue is the average of those synthetic ensembles, and we're comparing the gray to the blue line, which is the observational trend spreads. And you can see that none of these spreads fall within the same range. You do have, again, in the IPSL model, this ensemble member falls within somewhat of a close range, but you have 31 other ensemble members that are not doing that. So that is why you cannot just pick one ensemble member, because if I picked this one ensemble member, I would maybe conclude that yes, this model is capturing accurate information, but the rest of the ensemble members aren't doing what they're supposed to. So this strategy really helped see how poorly these models are doing. So some conclusions I came to is that no model is capturing what is seen through these transport observations. No model consistently captures recent positive trends in Bering Strait transport, and some models show variability similar to observations, but most of them overall do not. So moving on from here, I'd like to create spreads for other models. I possibly may have picked the 7 that aren't doing what they're supposed to. There's 50 plus other models that may be showing some positive results, but overall these 7 are just not capturing anything. So I'd like to give a huge thank you to Hannah for helping me with my first research project. I'd like to thank the other AOS Summer Research Program students. It was really nice to work with you guys and meet you. And then I'd like to thank anyone else who has helped me with this project along the way. So thank you for your time, and I'm opening to questions.
You made the point earlier on that the Bering Strait is very narrow and very shallow. And just naively, it seems like the main thing that should be driving the transport through the strait is just the sea level difference across the strait and any wind stress component along the strait. Are there other variables? And if not, or even if there are, is it possible to look at why the different models are not getting those variables right?
So I have looked into a little bit of this, and it could be due to the ice melting, with just such frequent ice melting, the water pushing through is at a greater volume flux. And then what was the second part of your question there?
Basically, whether, I mean, if it's really as simple as what I just said, where it's just two variables, the sea level height difference and the wind stress, I don't know what else would be forcing transport through that narrow opening, but if that's it, or even if there's a couple more, could one look at how the models are doing with those specific variables and try to understand why the models are disagreeing so much?
Yeah, so in other papers that have looked at the similar topic, it may be an idea that these models need to be tuned and calibrated to even work in this area, especially the MyRock 6 model. That was something that a lot of people noticed was an issue, because as you can see, this model isn't capturing any, even just a large variability within. It's just completely down below and not capturing anything. So that is what a lot of people have concluded, that maybe even that model specifically just needs to be tuned to be calibrated with that area.
Yeah, so it definitely is the pressure, the sea level pressure difference that drives the transport. And so that is something that people have specifically looked at in terms of why they don't capture these trends. And what we're seeing with the Woodgate more data. That would be a good next step.
It's like, I mean, these are all 1 degree or 2 degree models, and the Bering Strait is probably smaller than the river resolution, so it seems to me like it would be very difficult for those models to capture the physics of that strait, and maybe this would be a good case for downscale, and, driving the models with a higher resolution plan. Use those models to drive a higher resolution plan, because you're comparing it with a point that
Yeah, that's a good point. I never even thought about that.
Thank you to our speaker. Now, our next speaker is going to be Juan Perez. Juan Perez. No cambio de apellido.
So, good morning everyone. I am Juan Colon. I am an undergraduate student from the University of Puerto Rico at UW-AOS. For this summer, I am in the AOS Summer Research Program, and in this case, I was assigned with Professor Angela Lames-Corraliza, and my project is about the effects of large-scale dynamics on African easterly waves and its relationship to tropical cyclogenesis. For my motivation for this work, African easterly waves are the most common early stages of a tropical cyclone. Then we don't have like that much explaining on the predictions of the behavior of the African easterly waves and its relation to a larger scale phenomena. So by this reason, I wanted to pursue a research in this topic to address that lack of knowledge there. For the goal of this study, as I stated before, is to evaluate the effects of large-scale climate variability events on African easterly wave development. As a result, contribute to better predictions on future hurricane seasons. Getting more in depth in what is an African easterly wave, these are waves that are a cluster of mesoscale convective systems that organize and generate due to the African easterly jet that is represented with the blue arrow, and you can see how it has a low pressure through area. There are the MCS forming, and then you have there is shallow convection there, and then you again, like when they are approaching to the western coast of Africa, they become more. It depends on the strength on the African jet, but they become stronger. And then when they in their path on the Atlantic Ocean, some of them become tropical cyclones. For the large-scale conditions studied in this research, we have the ENSO effect in the Atlantic, tropical North Atlantic SST anomalies, and North Atlantic oscillation NAO, and the Madden-Julian oscillation MJO, that is a intraseasonal variability, climate variability phenomena. For the effects of the ENSO in the Atlantic, for the first part we have to El Niño and La Niña are seasonal events from 2 to 7 years that have teleconnected effects in the Atlantic basin. So as we can see in this figure, the Niño or La Niña events alter the normal Walco circulation. So with that in mind, we have the El Niño conditions are characterized by strong wind shear and cooler than average SSTs over the Atlantic. And with the Niña conditions, we got decreased wind shear and warmer than average SSTs. Also for And as well, several studies such as Camargo 2007 have been shown evidence of that relationship between the ENSO and tropical cyclone development. So here we are addressing more towards that early stages of African easterly waves. For tropical North Atlantic SSTs, we have to keep in mind that sea surface temperature modulates the amount of water vapor that goes into the atmosphere, thus regulating the convection that forms over the ocean. SST over the main development region, which is represented with that red box there, are strongly associated with tropical cyclogenesis. For the Madden-Julian oscillation, this is an easterly moving disturbance that completes a period around the planet to 30 to 60 days. The MJO consists of 2 regions, one convection enhanced region and one suppressed convection region. The location is determined by the convective phase. So when we are looking at the, let's see, like the phase, this is like the schematic for the processes involving within an MJO wave. So you have the stormy and wet and all the instability over one part of the MJO. In the other part, you have the downward motions enhancing dry and sunny conditions. For the Madden-Julian oscillation phases, we got here a representation of precipitation anomalies within the phases of the MJO. So you have phase 2, and then it is moving westward until arriving at the eastern Pacific and approaching the Atlantic. But when the MJO, when it enters the Atlantic, it weakens so much. So there is, here we address more like the active phases of the MJO, although the 8 and 1 phases are more related to tropical cyclone development. We wanted to make sure that continue with the African easterly waves. And for the others here, we got we determined with 2 variables, the RM and 2, the real-time multivariate MJO, and the other is representing, both of them represent the cloud amount and the upper level winds and lower level winds intensity. So this is here with the searching for the amplitude here. You can have the intensity, both the intensity and the location of the MJO. So as you can see, you have 8 and 1 phase. The MJO is over Western Hemisphere and Africa, and then 7 and 6 over the Western Pacific, 5 for maritime continent, and then 2 and 3 goes over the start on the Indian Ocean and Eastern Africa. For the North Atlantic Oscillation, the NAO involves fluctuation in atmospheric pressure at sea level between the Icelandic low and the Azores high. A study made by Zhang in 2022 found that a positive NAO index in spring can induce negative SST anomalies in the North Atlantic remaining into the summer by ocean memory, and then based on this result, the analysis for the NAO in this case was focused in contrasting the spring season indices to the developer's activity. So for the methodology employed in this project, we got the first step. The developers were separated from the non-developing waves using the vortex tracked method of grammar, and then we retrieved the data for each of the phenomena studied, and then the processing the anomalies and indices using the Python package pandas. Now we go to the interesting part. So for the result and discussion, we got here a linear 3.4 SST index where the blue boxes represent active seasons in terms of developers, and the red box represent inactive seasons in terms of developers. For most season, as you can see, most season with more developers than average relates to neutral or La Niña conditions. So see more in depth, we got the Niño index average. So negative 0.5 and below represent a Niña conditions, and 0.5 and above represent Niño conditions. And in between that values, you have neutral conditions, so no alteration to the welcome circulation. And then we find here that more developers relates to neutral La Niña conditions, and on the other hand, inactive seasons such as 1992 and 1997 are more related to zero, developed to neutral, or a very strong positive index like you can see in the 97 hurricane season. For the tropical North Atlantic SST, generally the SSTs in the tropical North Atlantic are showing a positive trend. So you can see the warming trend here in the tropical North Atlantic. And active seasons are more frequent during warmer years. So you can pair that 2005 very hyperactive in terms of tropical cyclones, and also you can see in terms of developers too. You can see here 2005 and 2011, 12. That years were really active in terms of tropical cyclones, so it also coincides with developing African easterly wave. Remembering developing African easterly waves are the most common, but not the only phenomenon that can trigger a tropical cyclone. For the North Atlantic Oscillation, a strong correlation between developers and these phenomena wasn't found, but only with in 1992 we found that very strong positive index in the now during spring season has in effect in the 92 has a correlation in the 92 season that has zero developers, but it wasn't as strong with other seasons to just tell that the NAO has a strong relation to them. Now with the intraseasonal events, because the Matt and Julian is more intraseasonal, it can change from weeks or from days. You can have one developer with one phase and so forth. Developers are more likely to develop during phase 2 here, as seen here at like 16.5% of probability. This result can be related to the phase 2 of the MJO located in near Eastern Africa. So it maybe is enhancing the African easterly jet, so promoting more robust African easterly waves. For the summary and conclusions, hurricane seasons with above average developers have become more frequent since 2000, The El Niño and Southern Oscillation coincide with most developer active seasons during La Niña or neutral conditions, whereas El Niño conditions triggers inactive seasons in terms of developers. For the tropical North Atlantic SSTs, a positive trend, warmer years are more conducive for African easterly wave development. And for the North Atlantic Oscillation, it didn't see like strong relation to just point out or having in account when analyzing this African easterly wave development. For the Mellon-Julian Oscillation, the phase 2 was the most conducive compared to the other active phases that goes from 1 to 8 to have a developer. So these findings can help to the better understanding of the response of African easterly wave to large-scale climate variability. For future work, I want to perform an analysis also adding intraseasonal events like Kelvin waves, effects on the African easterly waves, and evaluate possible relation between large-scale climate variability events studied and estimate the effects that the West African monsoon has on the African easterly wave development and the African easterly jet. So this is all for today. Thank you for your attention.
This is just more like a comment. I think I would like to see the connection between Idamis research and your research, because I think it should be like a correlation between these results. I don't know, I just think it's just really interesting to see.
Yeah, and that's on part with I want to just address here that search for the relation between that event, because maybe one event, we know based on the results that both the Ensemble, the tropical North Atlantic SSTs have more impact in African easterly wave development than Mellon-Julian Oscillation, because the Mellon-Julian Oscillation is basically all year. It can be like phase 0, so you have more active phases in only determined times. So you have more present, more relations for the ENSO and tropical North Atlantic SST. So it would be interesting to just combine the result of Idamis with the central coastal in Niño and see if they have like an effect also in the African easterly jet and subsequently the African easterly wave development.
The relationship between the MJO and the easterly waves is really interesting. I was wondering if you knew what the time scale to communicate between the MJO in those phases and the easterly waves, because I would imagine there's some lag between when something happens and when Africa knows about it. So are you seeing something from a different phase that's only getting to the easterly waves, or like getting to Africa later and now it's in phase 2?
Oh, yeah. So for the analysis with the African easterly waves, I just addressed the exact phase that day that the developer became a tropical cyclone. So there can be much more things like in account to address the intensity that developer reached then, or if that developer was weak, and then because with the MJO you can have a phase one day and then it changes the other day because it's an intraseasonal variability event. So you can have like that fluctuation. I hope I cleared your.
And so it's only when it becomes a tropical cyclone? And
yeah.
So can that happen like even weeks after the wave forms as well?
Yeah.
Okay.
One analysis that wanted to be done was the lag regression, but there wasn't enough time to do that. But the lag regression would have been interesting to see, like the effect that the MJO would have, like days before or days later than the tropical cyclone developed.
Yeah, I think that would be really interesting.
And also, well, in your line, we can assure also for the, I didn't add it as future work, my bad, but I want also to do more, go more in depth with the intensity and yeah, some studies have shown that phase 8 and 1 are over Africa and over the Western Hemisphere and can induce a tropical cyclone, but you can see that more in depth and study if that is a lag regression or if there is a not direct correlation, but it's, we can make it with other processes involved.
With that, let's thank our speaker. move on now to our last speaker today, which is Peyton.
Hi everyone, my name is Peyton Camden and I am here for the summer working on a project that shows the relationship between GOES-16-derived cloud products and lightning products. So really quick outline of my presentation, a little bit of background, what we're aiming to do, the data we used, a little bit about how all over the place my methodology was, some of our results, and other future avenues for research with this project. So a little background about myself. I'm a senior meteorology major that goes to Valparaiso University. I'm originally from Romneyville, Illinois. I'm here for the summer as a NOAA Hollings intern, working with Dr. Andrew Heidinger and Dr. Mark Cooley on this project. And so, what is the project? So, a little bit of background about satellite for anyone who may not know. Most people, when they think of satellite, think of visible imagery, like the image on the left, but there's actually a lot of other things that you can do with it. There's obviously channels that do infrared sensing, and so when you combine some of the visible image data with infrared data, you can actually derive some of the different properties of the cloud, such as a cloud mask, which is whether there is a cloud or there's not a cloud in a given pixel, or something like the image on the right, the cloud optical depth, which is how deep the cloud is and how there's a bunch of other ones that you can use. Those are primarily what we will be working with, not the raw data, but some of the products. And also on the satellites that are out in space, there's an instrument called geostationary lightning mapper, which is basically a sensor for any sort of light that comes through like at the top of the clouds. And so what it does is it kind of measures the amount of light that comes through the cloud and groups it by flashes and events to create lightning products that are kind of the equivalent of the cloud products. And so the goal for this project is to see if there are any interesting relationships worth exploring between lightning and some of the cloud products that are produced here in the building. And so this image is of the derecho in the Midwest on August 10th, 2020. But what we chose to use for our study was the May 12th, 2022 derecho. It's important because there were very high wind speed gusts that impacted a lot of people throughout the Midwest, and there were actually 6 tornadoes that produced higher winds that were not straight line winds. And so this is the day that we chose to use. Our goal overall was to use Python to create different analyses of the cloud products with the lightning products, and ultimately validate the accuracy of the cloud products and the algorithms that are being produced here in the building, and create kind of a baseline to build future research off of. And as a part of my Hollings program, another objective for me on a personal level was to gain a better working understanding of NOAA as an organization, the types of careers and things that you would do within a NOAA career, not just here and working with NESDIS, but also throughout the entire organization. And so the primary question driving this research was what cloud products are the best indicators of lightning and its potential. So the data that we used was obviously May 12th. We started from 18Z and went to 1Z on May 13th, so that's roughly from the early afternoon ending at like 8 o'clock. We had to choose this data specifically because some of the cloud products we used were only calculated using daytime hours, because if you have a visible observation, obviously, if you don't have sun, nothing's gonna be visible, and so because some of our products did use the visible imagery as part of its like input, we could only use daytime hour files, and so that's why this case worked really well for us, because most of it was done by the time night fell. And so for the cloud product data, we originally have CloudRx level 1 data, which is we had it in both in CONUS and full disk. Those are just the different ranges of the spans that we had. And we used the level 2 product, which are like cloud type, cloud mass, cloud optical depth, cloud top temperature, cloud top pressure and height. And those were some of the primary cloud products that we looked at. And for our lightning data, we used the level 2 data from the geostationary lightning mapper, and we had to match it to the grid that the ABI data was from. So we had to make like a gridded product. In the development of that is where you were able to get things like flash extent density, which is the main product we worked with, but also total optical energy, minimum flash area, and some of the other lightning products that come along with that. And so, like I mentioned a little bit earlier, my methodology was very all over the place. I originally started with just like some test data to kind of get my hands dirty with Python and how to create the data in a way, like load it in and reshape it in a way that would be able to do what we wanted to do. And so I spent a little bit of time seeing what figures I could create and what kind of calculations I could do with the products. And so from there, that was with just one time. Then I used SatPy very heavily within Python to help me do this. When you load in your data, they call it a scene, but because I was using multiple data times, it was considered a multi-scene, which is actually much more difficult to do computations with. And so I had to find a way to not only create a 3D array that could withhold all of the attributes when it was compressed, but also expanded along the time dimension as well. And then it had to be sorted and kind of made sure that all of the area attributes are the same, that all of the dimension times match, which when you have these sensors, they don't always start and finish their scans at the exact same time, especially if they're not matching projection scans. Like if we had CONUS data for our cloud products, which we did, and full disk scans for the lightning, we had to make sure that everything matched up there. And so this became a little bit bigger of a challenge for me than I had initially realized, and because we were on a tight time scale, my mentor Andy did provide me with a script on IDL to kind of help speed up some of these analyses. And so we looked at different types of bar graphs, histograms, and cartographic projections to see what the products were behaving like. And so here's just kind of an example of what some of my code looks like. You can see you have to load in the products. You have to make sure that all of them are blended together so it can function as a time series. You have to make sure that all of the location and time attributes are the same. And so overall, our results generally acted how the different cloud products, like specifically cloud type and cloud top temperature, did act the way that some literature has suggested it should, meaning that when clouds are comprised of ice, like an overshooting top, just an opaque ice cloud, cirrus clouds, those are more likely to have lightning than water clouds. And also that because of that, the cloud top temperatures are colder when you see more lightning. And so this figure shows that as you have a colder cloud top temperature, your mean flash extent density is going to be a little bit higher. And this figure kind of shows the same. The black line represents when there's no lightning, and you can see that the probability of lightning is generally higher when you have colder clouds, just because if you have no lightning, your clouds are more likely to be water, which is right around like 280 Kelvin. And then when you do have lightning, your clouds are more likely to have colder cloud top temperatures peaking around like 240, and then a secondary peak as well at 220. And when we look at cloud types, you can see that cloud type 6, 7, 8, and 9 are our ice cloud types. And you can see that the fraction of lightning here on the y-axis is highest for cloud type 6, which is your opaque ice clouds, as well as cirrus, overlapping cloud types, and overshooting tops having the majority of the rest of the lightning. However, the difference is that even though lightning occurs most frequently in cloud type 6, the fraction of lightning for each cloud type is actually highest for cloud type 9, meaning that maybe cloud type 6 is more common, so it is most likely to have lightning just based on how often it occurs. But when you do get overshooting type clouds, those types of clouds actually have a higher percentage of a chance of having lightning. So you've got like a 3.5% chance of a cloud type the overshooting cloud type having lightning, versus the second one is cloud type 6 is closer to like a 1% of all of that cloud type having lightning. So that was an interesting difference. And so this just kind of shows that even though cloud type 6 might have more lightning occurrences, it does not necessarily have the highest percent of all of that cloud having lightning. As you can see on the left-hand side, this image shows the mean flash extent density only when the cloud type is 9, and on the right, it's for all cloud types. So even though the magnitude of the mean flash extent density is higher on the right and has more flash extent density on average, cloud type 9 actually contributes a lot of the lower magnitude mean flash extent density. And so just to kind of summarize, colder cloud top temperatures lead to generally higher average flash extent density and a higher probability of lightning. Most of these lightnings are within the ice cloud types, and even though overshooting type clouds have a higher percentage per number of clouds that produce lightning, overall the number of occurrences is highest within opaque ice clouds. And so this was just the beginning of a study. There are so many different things that you can do with these, even with just the 4 cloud products that we ended up using in our final analysis and flash extent density. There's more lightning products, there's so many more cloud products that you could use. There's tons of ways to expand that. And this could also be expanded to look at like a temporal evolution, to do case studies on other types of events. This was just a convective event, but there's also non-severe events that you could look at. You could look at like daytime thunderstorms in Florida, or like lake effect snow. And so there is a lot of other work that can be done with this. And ultimately, if it is found that there are significant quantifiable relationships between some of these cloud products, hopefully they would be able to be made operational and used in some other programs like LightningCast to help better train machine learning models and other types of products that operational forecasters would be able to use. And so overall, I just want to acknowledge my 2 mentors, Andy and Mark. I couldn't have done this without them. And give a big shout out to Jolene Feltz and Steve Wanzong. They provided so much support on the data and coding side of things. And of course, acknowledge my funding is from NOAA through the Hollings program.
Did you consider in your work that the GLM is not a complete picture of lightning? You're only seeing something about yourself, so there's a lot more things that you can kind of do with a combination of GLM and, say, ground-based sensors?
Yeah, so we did actually consider that there is some not inaccuracies, but GLM isn't the full picture like you said, but that's just the satellite observations that we had. So that's why we're just comparing it to GLM lightning observations and not lightning in general. Yes?
So I think LabRex, it only identifies one cloud type per pixel, right?
Yes.
And you could very well have opaque ice clouds with overshooting tops underneath them possibly, right?
Yeah, that's
I'm
true.
wondering how much that is, particularly since you're looking at one case, it may be the opaque, ambles from other clouds that are obscuring overshooting tops that have light in them as well.
Yeah, I think you definitely bring up a good point. That is very possible. This was just an introductory analysis. I'm hoping that after the summer, Mark and Andy do continue working with this, doing other case studies and more broad data sets, so that something like that might be eliminated if that is existent in this case study. There's also different, because the algorithms are identifying it based off of they have like a certain algorithm that will classify it a certain way. It's always possible that they do update that algorithm. Other than that, I'm not really sure what more we could do to kind of compensate for that, but that is something to consider, so thank you.
With that, let's thank our speaker. Thank you everybody for joining, and I do want to offer a final round of applause to all of the people who presented today. We do know that we had limited time for questions, but now we have lunch. Everybody can join, and if you want to chat with the speakers some more and ask all the other questions, feel free to do so as well.
Okay, and we'll be back here around 1 for just a final little recognition ceremony, but if you have, other things you need to do with your day, I understand, but we will be doing that with our students, so enjoy, and thank you. You probably feel the relief now.